Okay, everyone. So welcome to this talk about the Zephyr RTOS. This is an open source project that we are quite excited about and we use at the company we work for. But the title, Power Tool for Constrained Devices, it's kind of to address the thing that we see that many people start working with free RTOS. Zephyr RTOS there's a bit of a learning curve. So once you passed it, they are really passionate about it. Think it solves a lot of their problems in their development. But for many others, when they go into a situation where they have to use Zephyr, they are kind of a bit overwhelmed and a bit resistant and often don't understand how things are pieced together and what purpose they have. So this will be less about RTOS and more about the tooling around the ecosystem and what the possibilities you have there. So let's talk about us. So I'm Eirik Midttun. I work at Nordic Semiconductor. I've worked for quite a few years as a software developer. Now I've said, as we say, I've gone over to the dark side, so I'm in product management. I work as a technical product manager, spending most of my days talking to customers, answering emails, and also talking to R&D and explaining to them what is it that we should make. And with me I have Balaji, who is a senior R&D engineer. It's actually does stuff, so you can tell what you do.
Yeah, I've been stuck in the bright side for a long time now. So doing embedded software development for the last 11 years. Before that, also doing some software development, but for larger embedded devices. As you can see, I'm having a hands-free mic, so I will be doing the demos.
But first, a bit more talk. So there's a bit of mixed audience, so I'm not sure if that constrained devices was absolutely clear to everyone, but I'm going to explain what I mean by it and also a bit of sort of history and what kind of problems we have in this domain. So 15 years ago, that's kind of started my career. I worked on 8-bit MCUs, 16 megahertz. I say 8051 because it wasn't really 8051, it was just compatible. That was a free IP, so it was kind of popular at that time. And 60K of RAM. I had less when I started, and 1K of RAM, 16 kilobytes of flash. And this is the most recent product we have. This is radio MCU with 128 megahertz Cortex M33. It's actually a dual core, so this is kind of for the main processor, those numbers, and there's an additional one with its own flash and RAM. So, it's a lot of things changes over the year, but I still feel I'm in the same industry. So, because some things are the same. First of all, it's always been a price-sensitive market. So the prices on both those chips 15 years ago and now goes from less than $1 for one chip up to a few dollars. When it goes close to 10, and it's quite an expensive one. And this is because this is the type of product that is produced in large volumes, and dollar cents can make or break a deal. So price is always important. I just also, picture is not very clear, but I mean, this is flash memory, and the price kind of scales with the area of this die. So memory is really expensive. So if you can compact your code a bit and make the program smaller, then that has actually, it pays off itself in money. That said, that gets less of a problem as the technology nodes gets more advanced and you can shrink it. But size also important. It depends on the type of product, of course. But there's one of our products in this watch, for example. So then they measure in cubic millimeters. So depending on market, that's also important. Power consumption, some are plugged in the wall, but lots of these things runs on batteries, and how many months or years you can run on CR2032 point cell battery. That's kind of a benchmark when it comes to power consumption. One thing that is increasingly important, wireless connectivity. That's kind of business we're in, but that we're seeing that more and more because everything is IoT. IoT is kind of an unfashionable buzzword because it's more becoming the reality. So we see that. Upgradable software features. So at the basics, it's that you have a bug and you can fix it by uploading new firmware since you have flash. But actually, customers who design products now with more flash than they initially need, but then actually sell upgrades. So they get the physical product out in the market, and then they start developing a software feature that they kind of sell and charge a premium for, or it can be services and so on. Security, it's important in itself because there are lots of security issues with connected devices. But there is also legislation. So there's something called the EU Cybersecurity Act. There is a similar act in the US that has a very long name, so I don't want to say it. But yeah, there's there. Finland, Slovenia. There's some countries that have labeling programs. So when you buy a washing machine, you can see like if it's A class, B class, or how much power consumption there is. And they have similar programs for security, so you can actually have a label on your product saying if it's secure or not. So you can do it. You should do it for your own sort of good and reputation, but soon there will be no way around. You will not be able to sell products that are insecure. Yeah, so that's a bit of background, and then yeah, as a software developer, I think this is was true and is still true for our business. Language, that's mainly C. Still some assembly, you can counter that, and yeah, C++ and Rust is kind of getting more popular, but it's still a fringe. Mainly bare metal. So if you go back to the image where I showed 15 years ago and now, I mean, when I started, I could probably write the whole application myself, but that's no longer true. But that's kind of way of working is still common. So yeah, bare metal, but you see also increasing use of RTOS because there is no memory and the application are getting more complex. You don't really see any common solution to dependency management. So when we talk to customers, they have usually built their own in-house solution to that. So entire systems based on, for example, free RTOS and lots of scripts around. Target testing is another thing. Like, yeah, if you code on a PC, you can compile and run your code quite fast. If you want to test something, you often have to test it actually on the target. So you have to compile, program it to your target, and then see what output comes over serial interface. Yeah, and that's kind of the developer flow. Then you also run regression testing on target. So it's quite common to have a good knowledge in C and Python just to run regression tests and test rigs and so on. So yeah, it's a bit chaotic. There's a bit of lack of standard way of working. So yeah, there is a project. It's now in the Linux Foundation. It's called Zephyr RTOS. And they actually have a stated goal of becoming the Linux of microcontrollers. So let's stop talking for a bit and let's move on to a demo. So we're going to start very simple. Blinky, that's a blinking LED. That's kind of the hello world for embedded applications.
You see something? Yeah,
Yeah,
you see my screen.
I see a pointer.
Good. Just gonna be explaining a bit about the board. And
I think the screen is black because it's
yeah, that's fine. It's just don't worry, it's gonna come up. I need to enter the password. So I'm gonna be using the 52840 development kit here. This is the thing that we sell to customers, developers who actually want to prototype and play with the implementation. So it has a debugger, the SOC, and lots of GPIOs, some buttons and LEDs. So the simple example is just blink an LED. So it's going to be periodically blinking an LED. It's going to drive home the concepts of how build system works in Zephyr. We're going to talk a bit about how to configure the application. Yeah. So I'm going to be just connecting this one to my laptop here. All right. So let me just clear everything here. So I'm in the Zephyr folder. Basically, this is a checkout of the Zephyr repository. Do you see it? Yeah.
Yeah, we can see it.
Yeah.
If you can increase the font, if that's possible.
I do it, but it doesn't seem to increase there. Just let's see how this is. Yeah, it's better.
Yeah.
So here I typically have some folders here, and we have some samples. We have drivers, kernel, everything. So I'm going to be going inside the samples folder, and there are some basic samples. I'm navigating into that, and there's a Blinky application. This one basically comes out of box. So here I'm going to be building the application. I'm going to be using a tool called Vest. I think we will talk a bit about Vest while
yes.
in the next slides. Yeah. All right. So I'm going to be saying Vest. Let me just clean everything here. I do Vest build -b stands for board, and the board is NRF 52840. DK stands for development kit, and the SoC that's on the development kit is the 52840. Therefore, I'm going to say NRF 52840. So the notation is that first you get the board, and then you have the SoC. You can have multiple SoCs on the same board, or different board with the same SoCs. You can actually combine this.
So we'll show this later, but I mean there is a concept of development boards and actual hardware in the package. So.
Yeah. So I just started the build here. So what happens is that the Vest triggers CMake, and CMake is trying to find the compiler. I don't know if you're familiar with CMake, the build system, but it tries to find the compiler, the assembler, and tries to set up the rules for you. And then Vest also invokes a Ninja, which is a generator, and then it builds the final executable. You can see after it's done building, you can see the memory region, the flash, the used size, the region size, and how much is used. So it's a Blinky application. It's a very small application. Therefore, it's only 2.17% of flash that's used, and the SRAM is 2.91%. So it just gives an overview of the final executable itself. I'm just scrolling quickly up to just show you the output here. As you can see, it's the Blinky application. Trying to find Python. I try to find Python because Vest is a Python-based tool. And Zephyr version that's using this. Yeah, a bunch of other things. There's something called device tree. That's a Linux/Zephyr concept. We'll go into that a bit later. And there's a toolchain that it's using. So Zephyr offers a toolchain. It's basically a set of compilers and assemblers for different architectures. So right now it's picking up the toolchain from here, and then it's building the application. So the flash, basically I will just do Vest flash, and it identifies a runner called NRF JProg. So that's basically the runner that Nordic Semiconductor produces, and it's a runner. It's a programming tool for all the NRF boards. And I need to connect to the UART as well, so you can see what's happening. My PC seems to be stuck. Oh, there you go. Doing something. I think we have a demo effect here. Hold on a second. I just killed it.
As always, the demo effect.
Yeah.
Remember to include the USB device and
yeah, I did. It popped up and everything.
Okay.
I even tested this before we started, of course. All right, I'm gonna just pull it out and then pull it back. Put it back in.
We actually ship it as part of our SDK, and yeah, and of course that's what we build, and we actually contribute back with, you know, whatever is taken in from Zephyr, whatever improvements we can provide, we contribute back.
Yeah, so it worked this time. Had to plug it out and plug it back in, of course. So what it did is that it tries to flash this hex file and verifies the programming, and then it applies a pin reset. It's just to reset the whole thing. And using the serial port, you can actually see that the device booted up. This is the boot banner of Zephyr itself. Right? Shall I walk them through the?
Yeah, we can. I mean, I talk to customers, and they always say, like, you know, RTOS seems like it's huge, and we're using bare metal, and that's really, really slim. So, you know, will this fit? You know, oh, okay, we saw the final size, but should we show them the ROM report?
Yeah, sure. So here, if you go into the build folder, which is the build folder where it has all the symbols and the hex file listed. If we just type Ninja, which is the generator tool that I talked about, and then you type ROM report. So it's basically a target. It's going to split out how much space your individual modules are occupying in the final executable. So basically, this is a table.
Oh, did you see the kernel? Or?
Yeah, sure. That's this one.
4.6 kilobytes. Yeah, that's okay.
So that's 20%, 20.37% of the final executable. So that's what the kernel takes. Yeah.
So should we see how we remove feature if we don't need it from this?
Yeah, sure. So we saw the boot banner, right? So the boot banner.
Yeah, we don't need that in production.
Yeah, no, we don't need that. So that's probably up there. No, it's not here. There it is. The boot banner is like occupying 24 bytes. Let's say we don't need it. So the easiest way to do that is by using a tool called menu config. So if you open a menu config here, it's also a Linux concept, right?
Well, that's a menu config is command, but the tool is kconfig. Yeah.
Yeah, the tool is kconfig. Right. So if you open menu config, it presents you with a GUI where you can actually select and deselect features. So here there are a bunch of different things. You can actually search for the feature that you want to disable by using Vim shortcuts. Like, so a slash will pop this menu, and you can actually start typing whatever you want to type. So here I'm going to type boot banner because I know it's boot banner. And then here it says it's selected. So I'm going to just say I don't want it. I press a spacebar and I deselect it, and then I save it, and then I do a build again. So it's going to kick off the whole build system again, and it's going to produce the final executable. So we can clearly see that it reduced some size here. But let's look at the partition manager report here, or the ROM report here. So you will not be seeing the boot banner here. So I cannot show the thing that doesn't exist, but I just have to tell you that it's gone and the size is reduced. So that's one small example of how you can tune things in the final executable if you want to remove stuff. Yeah, you can turn off logging, for example, asserts. All this you can do using menu config. That's all. Okay.
So back to talking a bit.
Oh yeah, sure.
Okay. So now you saw it in action. Just have a little recap of what we saw. So there are a couple of components in here, or systems involved to build a project. So there is a kconfig, which is kind of a configuration tool. Use it to include the software components that you need in your build. It's the same tools basically that's used for Linux. So there's always some Linux flavor into the mix here. Then there's a device tree. That's a bit harder to demonstrate, but that's kind of what we use to define hardware. So it's like a hierarchical structure. So you can have, for example, an I2C bus, and you can define what sensors are connected to the bus. So Linux uses the same in their system. There's one difference here, that this that device tree is run at compile time, and it will generate like a sort of ready-made header file. So there's zero overhead to this. It will just define it, and it's very practical if you have one code base that runs on different target that might have some slightly different I/O settings or different sensors and so on. When you start on this little thing, I think device tree came a bit after kconfig, so something that should ideally logically be in device tree might be still be in kconfig. That's being worked on, but don't be surprised if you see some of that. Then a CMake and Ninja, which are build and configuration tools. So all this is kind of controlled by West, one tool. And a nice thing, West is implemented in Python. CMake is cross-platform, so basically the whole toolchain is cross-platform. Works on Windows, Linux, and Apple products, Mac. Yeah, we could talk a long time for this, but I'm not going to speak a lot about this. But there's a diagram of the application and the different components, and as you can see, there are quite many. So there's a kernel which is you can have preemptive and cooperative threads. One nice thing about this one, which is not necessarily found in other ones, is the integrated power management. So it knows quite well about power management in microcontrollers. There's an integrated driver interface with its own API, quite a rich set of services. It has network stacks for IoT and connectivity stacks, which is you can connect directly Bluetooth, Wi-Fi, USB, and so on. It's all included. But the point there is like kconfig is really handy for such a rich set of features. The alternative is, includes hacking your Mac files and manage all that. So yeah, it's really a really different way of working. There's another thing also, like kconfig sort of makes you configure the code base and the subsystem in Zephyr, but you can also expand it. So, or you can there's also addition to it basically. So there's the main repository, which is Zephyr Project /Zephyr at GitHub. And if you go to the root of that project, you'll see something called West YAML. And that will actually make references. So I have the first line after the comments here, where you can have named repositories and git hashes, which is a revision. And this pulls in code from other repositories. And there are things that are kept outside for various reasons, either historical or because it makes sense. For example, vendor HALs, so the hardware abstraction layers, is typically maintained by silicon vendors and maintained in all repositories, and the system sort of pulls that code. There's a secure boot implementation called mcboot. That's in a separate repository. File systems are typically picked up like this, and then there are various libraries like LVGL is a graphics library. OpenThread is an implementation for thread, which is integrated. So there's more project. And one nice thing here is that you can also expand it. So you can make your own GitHub repository with the same structure, with the same YAML file, and you can use West to put in Zephyr and all the dependencies in your project. And then you can add your own things to that project. It's actually what we do in our SDK that we distribute. So that has the YAML file, and Zephyr is one of the dependencies. And then there's a few other ones. So yeah, just to talk a bit about that one, but now we get a bit more advanced.
So yeah, so here we will show a simple demo of a Bluetooth application that's running on the same board. Since this is a BLE board, so you can actually build and run Bluetooth low energy applications on it. So I'll try to build a board, build an application, a test application, and then I'll fire some commands, and Eirik will connect to that from his phone, and ta-da, we have a demo. So we'll try that. I think this will work smoothly this time, but that's the famous last words. Let's see. So I'm going to go into our SDK. No, actually, no, this is not our SDK. It's actually the Zephyr itself. It provides a test application. We're going to test Bluetooth, and then there's a shell application. And here I'll just do a clean. I'm going to build. I'm going to use the same build command. Remember, it's the board and then the chip. I'll do this. I have the serial port open, and it's ready to listen to what this is doing. So here it built the application. I'm going to use REST tool again to flash.
We did a dry run on this one, and actually the plan was to show sort of like you can show the mobile phone screen on the screen here, but there was a network issue, so it didn't work. So I just have my phone. It's a bit little, but it's the best we can do. But this is the NR Connect app, mobile app, which allows you to scan for any Bluetooth device and discover what kind of services it has and so on. And since I know Balaji is going to run this example, I have a filter on it, so he's going to call it shell, and I filter and name shell.
Alright, so there is a small issue with the baud rate, so I'm going to just fix that. Alright, so I'll just reset the device once. Alright, so it booted up Zephyr, and then it's waiting for some commands, right? So the thing is that this uses the Zephyr provided Bluetooth shell module. So that's something that you can use to receive commands from a terminal window. You can control it. You can write automated tests using that. So this application is built using that shell. Here it says please type BT init to initialize the stack. We're talking about the Bluetooth stack. So I'm doing that. So it's printing a lot of debug information here. Platform firmware, the stack version, yeah. So maybe there's a help. Yes, there's a help, and it shows the commands that that this application supports. So basically, anyone can write their own shell application, and they can write their own commands. BT is the prefix for all Bluetooth commands. So here you can, I think there's a BT help. No, BT. Let's say add, yeah, so tab works. So add create will create a connectable non-scannable advertiser. These are basically commands that you have to provide. This is as per the Bluetooth specification, so I will not bother explaining this, but if you have any questions, please ask me after the session about these specific commands. Creating I have to provide the parameters. And I'm going to quickly refer to my cheat sheet here, and that's the name add. No, that was another one. It's name add, yeah. Sorry, conscan. I've missed that one. Conscan name add, right? This is just configuring the advertisement. So now I'm going to say add start. This should start advertisement and should show up in Erik's phone.
Scan to begin. Okay. Ah, I found it.
So try to connect from that.
Yeah.
So here you can see that it got connected. It's doing a bunch of different things. A file update is received, data length. These are all Bluetooth procedures. So these things happen when you connect any Bluetooth device to your phone. So it does this file update and connection parameter update. So there you have it, a live example. Yeah. And you can do BT disconnect. That will disconnect.
Got it? Okay.
I have not disconnected yet.
Okay.
Do that now.
Yeah, disconnected. Yeah, I got a pop-up.
So another example.
Yeah. Well, I think it's worth mentioning. I mean, it wasn't meant to be like a Bluetooth presentation, but it is cool to have something kit you can connect to your phone, and But and this shell, I mean the shell commands. That's actually first of all, there's a shell module in Zephyr, and there's a shell module for Bluetooth in the Bluetooth subsystem. And back when I talked about, they have target testing, you have to flash and program, compile, flash it, and then test out things. And this is really handy because, I mean, yeah, I have to admit it. I mean, lots of programming activities about learning. So you have a new API, you want to experiment it, you want to find out how things work, and even though you read careful documentation, it may not behave as you expected. So actually, this shell module exposes the whole API as a shell from your PC. So you can program this example, and you can just start running these commands, and you will see the behavior immediately. So I think, in our company, there's quite a lot of people who work with actually Bluetooth specification that are not released yet. And it's like, not only do you have to experiment something new, but I mean, it's not really ready specified yet. So getting that instant feedback is actually amazingly powerful.
Yeah. So I also wanted to show the debug functionality here. So usually when we program, we want to debug, we want to connect and debug. I used to be using third-party tools for debugging, but GDB is as good as it gets here. So if I just type west debug, it's going to automatically identify what it needs to do to connect to this device. All right, it's a big one. Okay, maybe I need to move this a bit like this. Yeah. So so right now it's in an idle loop, right? But we can set up breakpoints right away. So it actually, what it did was it just connected. It started the listener, the server, debug server, and immediately connected to this device through that debug server. And you can see that this is the stack, and this is where it is, the threads and everything. So here, what you see here is actually a GDB dashboard. This is not that comes with GDB. It's something else that I had to install. It's open source as well. But I'll quickly show you how this works. So let me try to set a breakpoint in main. Since it's a real embedded device, you can't do a reset. You have to you can do reset, but it's a different way. You have to say mon reset, and then you have to say continue, and then it hits the breakpoint. So this is the first ever instruction it runs. Because I have this GDB dashboard, it nicely shows the registers, the expressions, the history, and the stack, and the threads that are running. So right now it's only the main that's running. And basically you can just step in, step out, and you can see as I step out, it's actually printing stuff that it's supposed to print. So the point is that we have the framework ready, and Vest nicely provides you. Vest is like a nice meta tool that you can use to do all the stuff that you normally do with an embedded device.
We've seen now that we've done a building and with Vest,
flashing,
debugging. We didn't show it, but I mean, it's also do the repository management. West update will be the demo for that.
Yeah.
So it's kind of like a Swiss Army knife, and I mean, back to like what is typically development of constrained devices. So there's numerous tools, and if you switch from one to another one, you have to learn. But there is one tool you have to sort of deal with, and the other tools are kind of under the hood.
I also use Vest to run unit tests, so it's very easy. So you just say the board is native POSIX, and then you run it, and it runs on the PC itself a bunch of tests that you create. Yeah. So I find it really nice. That's me.
Good.
Yeah. Sorry.
So we're gonna have actually one more demo. But before that, let's talk a bit about. So why should you choose this in your project? Because it's not like this is the only project out there. Around 2006, actually, was kind of lots of various options, and some have kind of faded out. Some are still alive, so that's Zephyr, but then there's Nutex, which is kind of still popular and widely used. Riot is yeah, it's also kind of in the same, I would say, in the same category. It's more popular in university cycles. ARM Embed was an initiative by ARM, but that's mainly centered on ARM, and then it's RT Thread, which is a Chinese initiative. Free RTOS and Amazon Web Services, they're doing something together to create a package, and what they're trying is like, the similar, like you have an RTOS, but you also have a driver module, you integrate the connectivity stacks into one common project. About this battery included term from Python, like when you download a software package, you get everything. It's not like you have to do free RTOS and then you have to use LVIP as an IP stack and you have to stitch this thing together. Yeah, modular design, lots of this come with it's like a predefined build system which I test and run regression against. So this, yeah, there's much to choose from, but we believe Zephyr is going to win. Let's just go through a few things that we think is required for wide adoption and at first long-term success. First, you need a fully open source implementation. That's what you need to get, like community engagement, cross architecture implementation. That means like silicon implementation. Permissive licensing. You also need a vibrant community, and last point might require some slides on that because that needs some more explanation, but that's actually also a very important point. So yeah, you have a cross architecture. I'm not going to say it, but it's Apache 2 license, so that's kind of the license part. But all these architectures are supported in Zephyr. So and I think with this level of support, the architecture is there to support yet another one, and there are other plans to add more. I think they cover the main part of the market, so I'm not sure how much more you need, but I mean the architecture is ready to accept. So ARM and Intel is kind of the most popular one, and lots of interest on RISC-V these days. The board support, like you saw that the B command, there's now 350 supported development boards in Zephyr. Actually, took initiative from a talk that was done 2 years ago, and at that point there was 200 boards. So the increase has just been amazing. Vibrant community, I didn't find a better illustration like that. We can show like how many Twitter followers and so on, but there's 69,000 commits so far, 4,001 forks, and there's about 1,322 individual contributors. And these are also numbers that kind of doubled in the last 2 years. So yeah, there's a lot of things going on. There's lots of people involved. It's also a organization that had members. So here's a platinum members. We're starting to get backing from quite some big companies. Yeah, just a bit of history. Like Intel and NXP Nordic has been platinum, like the 3 platinum members for a long time back. I think also known Oticon. I think they're kind of number 4, but that's a Danish company that is developing hearing aids and very quality focused. So and they've been in from quite early and is investing heavily in this. Google and Meta came on board about the same time, and Micro is it's a service company. Qualcomm Innovation Center, I think that's a subsidiary of the big Qualcomm, but it's interesting to see them there. And yeah, now we have T-Mobile, we have mobile operators in there. Silver members, yeah, I'm not going through all of these, but so you have Infineon, Silicon Labs, Texas Instruments. So we kind of have the big, like most of the big silicon vendors. It's just ST and Microchip, which I think is missing from this. But I know ST is quite active in this project also. Sci-Fi, they're making RISC-V MCUs. I can also mention Linaro, which is kind of the organization that made Linux useful on application processors, and they are also trying to do a similar job here. So yeah, vendor neutral governance. So we have members. They pay a subscription and they have some commitment, and it's also have a structure. So there is a governing board and a technical steering committee, which is staffed by the member companies. There's no single dominating companies, as you can see. There's some really big ones, but there's no one that is a lot bigger than the others. So at least one of the top ones. So it's kind of, you're on neutral ground here. If you want to contribute things, it's kind of, you don't have this risk of how to say, helping a competitor or yeah. I mean, when you look at the slides for the alternatives, you see Free RTOS is becoming the Amazon RTOS, and ARM Embed was an ARM RTOS. But here is kind of, it's truly a neutral one, and it's quite collaborative, and it's really good. Yeah, it's actually a good environment to work in. A few other things, which I think, yeah, I think many of the really open source ones project, like, you know, someone is just working without the structure, like what things that typically overlook is, yeah, how do you think about the product, like reliability and so on. So in Zephyr there is kind of a defined development and release process, especially the release process. They have a roadmap saying when it's going to release. There is a concept of a design freeze and a review process, so the quality is good. They have a long-term support program that goes in 2-year cycles. So every 2 years they release a version that they will maintain with patches for at least 2 years, which is important for the industry. And also security, so they have a focus on security. So it's an ongoing process. You have to review code. You have to make sure that they, you know, that they have followed good coding practices and so on. They also have done analysis of the code base by an external companies, and they found some issues. They've all fixed during the embargo time. In addition, they have a staffed research team that's a product security incidents response team. So that's a team that receives all security reports, and they do a triage and they decide if it's worth fixing and when and so on. And they also register as a CVE number authority. So that means a CVE number is basically a database code for a security security incident or security bug. So that's how you track, like, if you I dealt with security issues. So yeah, I think it's we can do questions afterwards, but let's have one last demo.
Yeah.
So it's a member. So it was one. This is actually a demo from one of the companies on the on this silver member list. It's called Memfault, and it's kind of a story like how it is to work in a community, because so Memfault is a startup company. The people that worked at Fitbit, Pebble, and those kind of companies, and they said their product is basically something done 3 times. They can log like debug information in the field and gather it, and it's it catches all these bugs, which can be for various reasons you will never catch them during development, but you can actually have a good overview, so show how it is. But they were interested in working with us, and if we worked the old way, I can just foresee there will be this discussion like who should bear the cost of integrating our solution? Like, should we want to sell it integrated, or is it you who sell the SDK and will gain from this? Are you going to do an integration job? And here it was really clear. They put code in Zephyr because that was neutral ground, because it was their interest. And we at Nordic made sure that it works with all boards and our products, and there was no discussion. It went really smoothly, and now we have it. So what Balaji is going to show is an example that has a tiny piece of code from Memfault, which everyone can sort of use for free as part of RTOS. It will catch faults basically, or fault events, and then I'll talk about later how to make money, but it's free to pick up and use.
Yeah, so I'm going to be using the 9160 development kit for this. I'm using this because this has an LTE modem. So what I'm going to do is I'm going to simulate a crash called a hot fault, or I'm gonna run an application that on the press of a button it triggers a Stack Overflow. The other button if I press the other button, it will trigger a divide by zero error. And I'm going to show you how this is sent to the cloud. So this one directly talks to the cloud. It doesn't need a phone or anything because it is directly connected to the cellular network. And this is the LTE-M network, the NB-IoT network. I don't know which one it's being used here, but I think it's LTE-M.
Mainly LTE now.
Right. So yeah, so that's about it. So you can see a SIM card here. It's a Telenor SIM debugger, GPS antenna. It has GPS as well. The LTE antenna and some GPIOs here. Yeah, that's about the board. All right, detector this time. All right, for this I'm going to be going into the NCS folder, which is actually Nordic Connect SDK. This is because the sample for this resides inside this SDK, the one that we made. But we will be using the features of the memfaults delivery. They have delivered to Zephyr. They also have their own repo. So everything is pulled in already and it's ready for me because I did prepare the repository for this demo, right? But it's really a few minutes of work, and then you have the whole repo on your desktop. So I'm going to be navigating inside the NRF folder, and here we have samples. And then here we have NRF 9160 folder. That's the name of the SoC. That's the name of the SIP, which has the LTE modem and an application core as well. Going here, here we have a bunch of examples. I'm interested in the memfault example. So go here. There is some build folders. I'm going to clean it up quickly, and I'm going to build. And this time, sorry, it's a habit. I'm using reverse search, so I'm gonna just type the command rest build -b nrf 9160 dk nrf 9160. So this is just the automatic complete that's kicking in, and hence the sound. And then I'm going to be building it for the non-secure domain because I'm building the application that will reside in the application core. That's the non-secure part. The modem resides on the secure part. The user is not able to access that.
Before we go into too much details, it's ARM trust zone, and it has a separation between secure and non-secure. So this is
all right.
Application is normally non-secure.
Good. So it does the same thing, and I expect a compilation error. That will not be a demo effect. That's not the one. That's the warning. Oh, it did build. I think that's because I already fixed it. Yeah, all right. I've already prepared it really nicely this time. So what I expected was a compilation error which says, hey, the project key is missing, but I already have provided it here. Therefore, it's a reverse demo effect. The thing about the project key is that this is the same key of the project that you have created in your memfault UI. So this is the memfault web UI. There you can basically create it's a bit slow. You can actually create projects. So you can, if you have let's say an asset tracker, you have a cat tracker application, you have a smart meter application. So you can basically create projects for each of those, and then you can monitor all your asset trackers in one project. You can monitor all your smart metering devices in that project. So any fault, any event, any reboots, that all get sent to that project, right? So I'm going to be using a project that I created already. I will not show you the creation of the project here, but feel free to drop by afterwards. I will show it. So the project is already created, and it's called NDC demo. And here, if you go into settings, you'll find the project key here, and that's what I provided in my my compilation. So it's just to link this executable with this particular project, right? And now I'm going to be flashing this one. I need to also connect to the COM port, which I've done now. And let it finish.
I mentioned the firmware is free, but I mean the UI, so that's where Memfault is making the money. So that's a subscription plan.
I was expecting a reset log here, but it doesn't show up for some reason. Hold on a second. The HDMI cable is pretty heavy and it's actually pulling the USB hub and it's creating loose contacts. Let's see. I think this is, yeah, I think that's the one. So it booted up and it connected its home network and it's connected to the LTE network, and time to connect was this. And it is actually sending an already captured data to Memfault. That's because I already had a crash dump stored there. But don't worry about that. I'm going to be creating a fake crash by pressing the button. So first let's create a Stack Overflow. So what that does is it basically recursively calls a Fibonacci number generator and it triggers a fault. I'm going to just open the source code as well, so you know what the source code looks like. Samples and 9160, and then the what's it called, Memfault. This one. So this is the main file for this sample. So there's a button handler that's implemented, and on the press of one button, it will trigger a fib of 1000 or 10,000, and that's basically a recursive call to another to the same function. And here it basically does a divide by 0 if button 2 is pressed, right? So first I press the button 1. It does something. It prints this ominous trace and it resets itself, and then it it starts Memfault again, Memfault sample again, and it's connecting to the network and it's sending some data. Let's see what the data is and how much of debug information is in that data. There is a learning curve here, but I'm going to quickly point you to where you will find this one. It's in the issues, and here you can see that there was something sent an hour ago. It's the same hard fault that I'm trying to create. And in about 2 minutes or something, you will see this UI UI showing the hard fault that I just created, right? So this is directly from the device to the cloud. So you can actually have thousands of devices deployed. That's usually the use case.
100,000 also.
Yeah, and then you can see everything here in one UI. That's what I think is pretty cool about this. So I don't want to wait for 2 minutes, but I'm just going to do a quick refresh and see if it actually reported the one that we just triggered. Still not. There is a small delay in the UI. So I'm going to quickly show you first what this one will have. So as you can see, this was first seen 2 days ago. That's when I created this project, and the last scene was 1 hour ago where I was preparing for this demo. And then typically this is how it looks. The zoom in level is quite high, so it's a bit weird, but you can see that the threads that were in operation, you can see that the active interrupt was the external interrupt number 47. That's the exception number 63, which is actually the exception number for the button. And then you can see the whole thing going in recursion, and yeah, it's basically showing you what exactly happened. You can see the registers, the stack pointer, all the registers that are in the current state of the registers, main stack pointer, and you also can see globals. So if you, let's say, create a global variable for some reason, and then you store some value into that, and then you can see that value here. So these are all the global variables that were present at the time of this crash, or the values of those global variables that were at that point of crash. So basically, it shows the whole cold dump.
It gives you some traces. Like if you have 100,000 devices, you can experience like maybe 100 of them fails in the field, and it's amazingly hard to reproduce that error. So at least it gives you a trace of what happened. Also, you can actually write to software so it actually can survive a reboot or something, and then you don't really know it's failing, but you can know that, okay, these devices are failing, yeah, every second hour or something.
Yeah.
So yeah.
So you also see some heartbeat data and reboot data. This is because we linked in the memfault's code, and that code is responsible for sending the heart rate, the heartbeat and the reboot information periodically. So yeah, I won't go much into that, but I'm gonna just check if the last issue, yeah, so now you can see 3 minutes ago this hard fault was triggered, right? The other button, if I press the other button, it's gonna trigger the divide by zero error, and that's gonna show up like this at the button handler in main.c line 138, and on line 138 you have this one. So it works. The one step that I didn't show you is the uploading of the L file. So that's very important. I skipped it for the sake of time. I'll show you afterwards. The reason why you need it is because in order to decode this raw data, memfault needs to know how the executable was built. So you really need to encode the upload the L file. That's a symbol file.
Yeah, you can connect the symbols to the actual data, because that would be binary.
Yeah. All right.
Okay, we don't have so much time left, so I think we need to. Yeah. So. Yeah. So. Yeah, I hope you liked the spell. I liked what you saw as much as we do. So yeah, just to finish off, please join the project. Use it, just download it and use the project if you think it's the right thing. You can also join as a member. That might be up to your company, and if you're interested in that, give us a talk, because we can also guide you there. Or you can just write code. So I pasted a link where if you just want to write code and contribute, that's also a way. Or you can just talk about it. So they have Twitter, link to Facebook, and they also have a Discord account that you can join if you want to ask questions. And actually that's very active, and you can get, it might be easier just to ask there. So already you've done some research, but I mean, if it's something that looks puzzling, there'll be someone there to answer for you. I think that's it, what we had for today. And yeah. Thanks for your attention. Questions?
Forgot to declare the gifts for questions.
Right. Yeah, we do receive questions also. No? License. It's everything in Zephyr is Apache 2.0. And I think also, for example, like on our SDK, we have a Nordic license, which is also quite permissive, but it's kind of restricted to our products. But we have, for example, a driver library, that's also Apache 2, and that's kind of a requirement for integrating it in the system. So that type of contribution is Apache 2.0 also. Could also mention that it's one of the features, like there's lots of things we didn't talk about, but one feature, I think it's available in the West, this is SBOM, software bill of materials. That has several commands, but one of them is actually go through your whole code base and see what licenses there is. So you can actually get the report of all licenses that exist in your code base, not only Zephyr, but other libraries you might have pulled in.
Eirik?
Yeah?
Can you tell them what it is?
Okay. You have an iPhone? Yeah, price for the first question.
There you go.
It's a Chipolo one. It's a Nordic product. You can use it to connect to your keychain, and it works to the Find My network of Apple. So if you don't have Android, you can use this gift. Any more questions? I think, I mean, when I hear that argument, it's kind of like, you know, we can't switch from assembly to C because C is generates too much code. I mean, the difference is very small now, and at least in our SDK, it's it's tuned quite well. So it's mainly how you deal with so the integrated power management is basically when you go into the idle state that actually make sure you turn off peripherals you're not using, you set the CPU in idle mode and so on. That has to be managed, and there's also quite a lot of coding. Yeah, it depends on the application code also. The world for us used to be simple, like, you know, do this or write code like this and then it's low power, but I think one of our most popular products is a power profiling kit, which is actually a power profiler that you can attach to your kit, and you can just see the power consumption live, and if you see anything abnormal, it's typically a sign like you should go in your code and check if you forgot to disable something that you're not using. But I would not say, it's not the RTOS itself, and if you go, yeah, okay, this is also way back for us at least. Many of our RTOSs was not tickless, so you always had to have a system clock running all the time. And if you switch to like a low power clock source, let's call it tickless OS, yeah, that's like the biggest difference from classic RTOS. But I think that we've never considered anything else, and it's always been tickless.
I have moved from bare metal programming to RTOS-based programming, and the challenge that I had was I was also seeing this heavy power consumption, and I found out that it was because that there were some features that were left on. Like one typical thing that I left on by mistake was the console feature, and which in turn triggered UART, and it always kept that peripheral on because it's expecting something from the PC. So turning it off helps it. But how do I find out that it was actually consuming power? By using a power profiler kit. You can actually see the idle current. So you'll see a spike when there's a Bluetooth connection or a LTE connection that's happening, and then you should really see nanoamperes of current. If you do see some microamperes, then that means something is on. So you can attach a debugger, you can see what's happening. You can open kconfig and see what peripherals are you turning it on. And we actually, for all these applications that we provide in our SDK, we also provide a low power overlay. So when you build, you can say West build and then overlay low power. And it's going to disable everything that we know causes high power consumption, and it's going to give you a very optimized, power optimized solution. So if you take a look at that, you can see which are actually consuming power. Yeah.
More questions? You can also come back with.
All right, thank you.